Interstellar travel is very, very, very difficult. The distances between stars are unimaginably large. So this video tries to shed some light on how difficult it is to get there. Is it even possible to have interstellar travel with the technology that we know? Why is it so difficult? If we can do it, what's the technology that is needed and what will not work? And what would it be like even if it were possible to travel to other stars? And can we tell if other civilizations are capable of doing it? So let's discuss a little bit about the possibility for interstellar travel. It might be possible, but it would be very, very, very difficult because stars are so far away and space is so empty. The difference between going to the moon, for instance, and the nearest star is like the distance between walking across town and walking to the sun. If you walk across town, let's say at about 1.3 meters per second for 10 kilometers, it should take you about 2 hours to do that. To get to the sun at that speed of walking, it would take you over 3,500 years to get there. It's something like 100 million times farther than any distance we have ever traveled with any spacecraft. Interstellar distances can be portrayed in a diagram like this one. This shows the distance from the sun to the nearest Earth-like star, Alpha Centauri A, which is a G naught star. It's about 1.5 billion years older than our sun, but represented in a logarithmic scale. So beginning with Earth here at 1 astronomical unit, Mars, Jupiter, Saturn. Saturn is at about 10 astronomical units. The Kuiper belt and the bow shock over here are a bit more than 100 astronomical units away. The edge of the local cloud of cometary materials, called the Oort cloud, is over here at about 10 to the 4 or 10,000 astronomical units, and 100,000, 10 to the 5 astronomical units. And Alpha Centauri A over here and its companion Alpha Centauri B, a K star, are just shy 1 million astronomical units away. You'd have to cross the interstellar medium just to get to the nearest sun-like star. So conventional rockets won't work to get there. We need a new kind of propulsion system if we want to go fast. And the easiest way to travel between stars may be to just go very slowly and live a long time. There might be ways to get around this. You've heard about wormholes and so on from popular science and science fiction. But all indications are that whatever technology you need to manipulate space-time is beyond our comprehension. So, what can we do? Let's ask the question first. What is propulsion? Well, we can begin by asking ourselves, well, why do cars and ships and planes and so forth move forward, and how do they stop? And why doesn't that principle work in space? So the idea is that propulsion is something that you push against. So stuff has to be taken with you to push against if you're going into space. That's how a rocket works in space. And then what determines the speed of a rocket? So the speed of a rocket is determined by how much propellant you use and the velocity of that propellant. So in space, you can reach the same velocity by taking either a lot of propellant and throwing it out slowly, or a little bit of propellant and throwing out fast. You get the same velocity. So with a car, you can reach 120 kilometers per hour on the freeway. Some cars do that faster than others. Quick acceleration or uphill travel takes power. And for a rocket, power is the same as the amount of propellant that can be expelled per unit time. So the more you can send out in a shorter time means that you have more power for the rocket. Escaping a planetary surface is like traveling uphill all the time by putting a lot of propellant out. But once you're in space, the power is not such a big deal. It's like driving on a long, flat, straight road. And the engine to get off a planet, like a rocket engine, is probably going to be different from the kind of engine that you use to get to another star. There are problems, of course. So the faster you want to go, the more propellant you have to carry. And the more propellant you have to carry, you have more weight, which makes your spaceship heavier. So a heavier ship means it's harder to accelerate. So the idea is that it's better to get as much propellant out as you possibly can to get there faster. So that's where this diagram comes in. So on the y-axis is thrust. So that's the amount of power that you get pushing out from the rocket, compared to on the x-axis, the fuel efficiency is how effectively you can get that propellant out. And you see over here on the left-hand side of this diagram, chemical rockets like are used by SpaceX and other space agencies like NASA and JAXA and Chinese and Russian space agencies and Indian space agencies. All of these different space agencies, they use chemical rockets. Nuclear rockets are good. They have intermediate thrust and impulse, but they can be messy. We'll talk about those. And then the ones with the best fuel efficiency have very low power. These are ion and plasma engines. You see the desired region over there is high specific impulse and high thrust, but we don't have a technology for that yet. So it is a huge problem. So different propellants give you different outcomes. So specific impulse, here I sub SP, is a measure of how much thrust you get out of each unit of propellant. So let's ask ourselves, how much propellant would it take to get to Alpha Centauri in 1,000 years? Well, of course, the propellant can't be more than the mass of the spaceship. So let's look at this. If we just look at chemical engines, the conventional rockets we have now, which are in this diagram here in the left-hand side of the diagram, their specific impulse is about 500, this diagram. You would need a mass of 10 to the 137 kilograms of propellant to get you to the nearest star in 1,000 years. That's more than all of the baryonic mass in the universe. No way. And this is the realm of traditional rockets like the Saturn V, ICBMs, and so forth. This is an old idea, going back at least to Jules Verne and Wernher von Braun. It was used in the Saturn V rocket program to the moon, and is being used in the Artemis program, also by NASA, to return the United States to the moon. So, how about nuclear thermal? Well, this is another kind of propulsion. It has a specific impulse of 1,000, You would still need more than all the mass in the universe to get to the nearest star. Uh, this propulsion seems really, really good for travel within our solar system, so-called interplanetary travel. It was tested in the 1960s for a Mars mission. Unfortunately, the mission was scrapped. But let's look at this in a little bit more detail. Westinghouse Industries uh, presented a mock-up of one of these nuclear propulsion engines, and indeed it was the inspiration for the spaceship Discovery from the motion picture 2001: A Space Odyssey. How about we talk about fission and fusion rockets? These have really great impulses, 5,000 to 10,000. Mass, however, is a lot. You need about 1,000 fusion supertankers, basically 1,000 oil supertanker ships of mass in space with fusion engines to get us to the nearest star in 1,000 years. Here are some basic designs. The idea here is that you have controlled nuclear explosions shooting out the back of the rocket, either from hydrogen bombs or some kind of fusion reactor. These things are within the realm of technical possibility, but again, would not get us to the nearest star very quickly. Then there's this idea of an ion drive. This is very interesting. You'd need something like 10 railroad tanker cars of xenon propellant to get us to the nearest star. These things have impulses of 50,000. And these things have actually been built. One of the first was the DS1 xenon ion drive quite a long time ago, a quarter of a century ago. It had exhaust velocities of 100,000 kilometers per second. But you need another source of power to run the engine. So it could be nuclear or something. And here's a picture of it. Here's a test of this xenon ion engine. And here is a schematic showing how it works. You have xenon gas enters a pipe here into a chamber, and then the electrons are stripped off of the xenon and it's accelerated here out. Direction of thrust is here with the blue arrow, because you have these induction coils here that strip the electrons off, and then the charged particles shoot out the back of the spacecraft. So the direction of travel is in the direction of this red arrow here. Pretty interesting. Then we get into the more theoretical aspects, matter and antimatter. If we could harness antimatter, we would get impulses of 100,000 to 10 million. It might work even at enormously high efficiencies, and the mass required would actually be very, very small. And there are no real designs, though, for containing antimatter, nor producing it, nor treating problems with radiation, because when antimatter and normal matter meet, they annihilate one another in a shower of gamma rays. And it costs $100 billion just to make 1 milligram of this stuff. So that seems pretty far off. Now, this is just for 1,000-year one-way voyage to the nearest star. Are there ways to do this without having to carry all this propellant with you? Well, it turns out, of course, that space is not quite empty as most people think. It's actually filled with gas. There are hydrogen atoms and atoms of other nuclides in any particular volume of space. So here's an idea called a Bussard ramjet. It was proposed by Bussard in 1960 using a spacecraft here that has a fusion reactor built into it and a magnetic scoop in front of the fusion reactor, which has an intake area here where a trapped proton, a hydrogen ion essentially, spirals into the magnetic scoop, and it's fused in the fusion reactor here and is sent out the back as exhaust. Well, maybe. So let's think about, though, what happens if you travel really, really fast in space. Things can get strange. No matter who you are or where you are, how fast you're moving and in what direction, the speed of light in vacuum always appears the same to you. So that sounds strange, but it has been verified many times. You cannot go faster than 3 times 10 to the 8 meters per second. So 300 million meters per second. The faster you move, the slower time passes for you. The faster you move, the more massive you get, which makes it more difficult to go faster. If you were to travel close to the speed of light to get to the nearest star, yes, it's 4 light years or so away from us, but to you, because of time dilation, because time travels more slowly, the trip would seem to take you only 2.5 years. Going 10 light years to, say, the star Epsilon Eridani, it would seem to you to take only about 5 years. To go 20,000 light years, like to the center of the Milky Way, it would be like 20,000 years at least on the Earth, from the Earth perspective. But for you, as a resident of that spacecraft, it would seem to you to take only about 21 years to get there. So this is important to keep in mind. Relativity is very, very, very strange. So here's a map of some of those stars I mentioned, Alpha Centauri here and Epsilon Eridani. So these are distances in light years from us. So we could get there if we had the technology to go fast enough. Here's Alpha Centauri right here and a star map. This star is extremely interesting. It's just a bit over 4 light years from us. It is a large star. Here it is in comparison to the sun. It is a bit older and a bit brighter than our sun. It rests right here off of the main sequence. This is a Hertzsprung-Russell diagram showing luminosity in solar units. Here's the sun's luminosity. Alpha Centauri A here is a bit brighter than our sun. It's a bit hotter. Alpha Centauri B here, which is a K star, is a bit dimmer and cooler. These two, A and B, formed at the same time in the same place. So they're a binary star system. The closest stellar object to us is Proxima. That's over here. It's an M dwarf. So it's not very sun-like. There could be planets around these stars. We know that there's an Earth mass planet around Proxima, even in the habitable zone potentially, but we're not sure about Alpha Centauri A and B. Possible planets at Alpha Centauri. So Alpha Centauri A has a habitable zone, not unlike the habitable zone of our terrestrial system here around the sun in our solar system. Alpha Centauri B here also has a significant habitable zone. At their closest approach, these two stars, they co-orbit one another. They're about 11 astronomical units away, so a little bit more than the distance from the sun to Saturn in our solar system. That means that any comet clouds or asteroid belts or Kuiper belts or things like that probably are unstable in these two systems. And so that is another big difference from ours besides age. Could be, though, that there are habitable planets there. If we had the ability to detect planets in that green habitable zone around either or both of those stars, I think it would compel the world to try to get there and to learn more. So that concludes this lecture about the difficulties in getting even to the nearest stars, but that shouldn't prevent us from trying. So if you'd like to learn more about our program, visit creo.space, and don't forget, hit the subscribe button below. Thanks a lot for listening.